Hello, everyone. We'll take a look at some of the machine learning tools in today's lecture. We'll consider probabilistic inequalities, and we'll take up Markov inequality, and which can be stated the the theorem. Let x be a positive random variable, then the probability that the random variable x can be bounded, the probability that the random variable x exceeds a threshold can be bounded above by the expected value times 1 by t. So the way we end up proving these kinds of things is by stating, let's say, the definitions. The definition of E of x is basically minus infinity to infinity x. This, by the way, is called Still-Lewis integral. The fact that this particular thing. Right now, you must have probably guessed like this cannot be like minus infinity, right? I mean, because the values only exist from zero. So I'll just take this integral from zero to infinity as opposed to minus infinity to infinity. Given that to be the case, like you can also split this since we need to consider the threshold t. We will probably split this as t to infinity d. And you can probably say that if the expected value is equivalent to these two parts, if we just write expected value and we take only one part, then obviously expected value is greater than, let's say, one of the parts, just by comparing. Now, if this is the case, then if we evaluate this, it'll be, let's say, t times. Now, this is again, can be written as probability that x exceeds t, right? Now, again, write it the other way around. Basically, what it says is like we have figured if a random variable x exceeds some threshold t, then it can be bounded about a factor of expected value. That's essentially the whole idea. Now, if we have to look at it in another way, we write it, we write the, let's say, the diagram of cumulative distribution function. And this is the probability value, and distribution function essentially accumulates value. It starts at zero because it's a positive random variable, and it gets close to, let's say, the maximum probability, which is one. Now this is the threshold t. Now if we write a complementary CDF and we had take the value t, t essentially hits the curve complementary CDF here. And if we join this line, this becomes the area of probability of random variable exceeding some threshold t, as opposed to the overall probability, which is probability that random variable exceeds x, right? Now, this area is basically, length into breadth. The length is t times probability. If we write this, essentially, you will have basically. I'm just restating this particular line once again, so that we say now this this can be, this is definitely less than this value. And if we recognize, let's say, this value, it's basically the expected value, right? So you can essentially write the area to be, what it's essentially saying is that this region will always be upper bounded above by essentially the overall probability value, which is the expected value. That's the idea of, Markov inequality. Now, let's say we have another inequality that we can consider called Chebyshev's inequality. And in Markov inequality, one of the assumption is that you can write it here. E of x is, that is, mean is finite, right? And we also assume that x minus ex variance is also finite. Now, given this to be the case, we know, let's consider this whole thing to be y, and this whole thing is y here, right? Now, we know from just, probability that, you know, this whole quantity exceeding some threshold is bounded above by expected value. Now, this is just, the definition of Markov inequality. This is like by Markov. This is basically Markov inequality. This can also be written as this is essentially variance, right? So you can write it as variance of x divided by t, or you can also write it as sigma squared by t, right? So yeah. Now, given this to be the case, if you substitute, let's say, what is it saying? It is saying, let's suppose if t is equal to 2 sigma squared, right? We already know that, what do we know? We know this value. Now, it's if we substitute, let's say, t to be 2 sigma squared, t to be 2 sigma squared, what will happen? What will happen is this whole, if we restate it, right? It's basically, right. I think this is not a whole square. This is supposed to be, this is just supposed to be 2 sigma squared. So this is again bounded above by half, right? So we understand the fact that if we, this whole idea is what exactly? This whole idea has got to do with the fact that the square deviation, this is stated here, the square deviation exceeds some threshold t, which is upper bounded by sigma square by t, which was what was stated here. Now, let's substitute more values and figure out what is the general form of this, right? The general form of it is, we came to know when does the probability is less than half. We can also write it in this sense, right? Rather than squaring, we can just write the general form in the absolute value. This again some random variable exceeding some threshold, basically saying that this threshold, these two things are essentially equal. This is important. Basically, what we're trying to say is the probability that some absolute value is greater than t is equivalent to some square absolute value greater than t squared, right? Which is again bounded above. This is based on whatever we wrote up until now, because we have taken this to be equivalent. Now, given this statement, if we say if in this particular scenario, if we take t to be sigma x, probability that x minus ex square is greater than, let's say, t square, right? Because this is t square, because this is t square and we're substituting this value here. So we basically say that this can be bounded above. So this is written as which is equivalent to 1. So this whole value is bounded above by 1. Now, if we say if t is 2 sigma, and we can say probability that t minus the absolute value square exceeds, let's say, 2 sigma, uh, 2 sigma whole square. It's not because it's t, right? Now, this would be, again, you restate it and say that this becomes square, right? Now, this is essentially, as you can see, there's a general form here that comes about it, right? Now, given this to be the case, like what else can we write? Can we write 3x? If we write 3, like if then the bound will be 1 minus 9, 1 upon 9, right? Now, if we say that the general form is some version like this, right? Uh, so this is understandable, right? Like this is the general form. Like anytime we have an absolute square exceeding some threshold t, and if t can have multiples of sigma square as the threshold, then it can be bounded above by 1 by k. Now, This holds true as long as variance is finite and deviation from mean is bounded by variance. So yeah, as we initially stated in the initial point, that this is all true only if variance is finite. Now, if we say what's the general form of this, so let's say if we state, let's say, what did we learn from the Chebyshev inequality? That absolute value exceeds some threshold, or this is equivalent to, let's say, the absolute value k times t exceeding k. All that is bounded above by the expected value that x minus e of x, which is essentially some version of, generalized version of a variance, or let's say the kth moment. And you can essentially say this is the the generalized form is the minima of this. And if this is all true when this is only true if let's say k is greater than 0. But again, this is like, let's say, the kth moment, right? Variance is the second moment, and if you cube the absolute deviation from the mean, if you cube it, that's the third moment. This is the kth moment, but this is all almost impossible to. I mean, it's very, very, very computationally hard to compute. But this is the generalized, generalized, let's say, version of a very well used inequality called Chebyshev's inequality, which is derivative of Markov's inequality for the variance term. And we'll look at other inequalities going forward. Hope you enjoy this lecture series that I'm going to do. Thank you.